Some interesting points to note. Okay, so notable points. Now, first of all, which row operations are we going, elementary row operations are we going to use at each step? Well, we're going to have a choice. Given an augmented matrix in front of us, we're going to have several choices of which row operations to use. And again, through the examples, I'm going to show you what criteria we're going to use in order to decide. Okay, but there is a choice. Okay, so for now, do it as you please. So pick whatever operation you think is going to work, but keep the following criteria in mind. First of all, what you want to do is you want to try and generate small numbers, and that's simply to keep the system or the matrix simple. We don't want to be working with large numbers. Another thing that I would like to suggest, I'm not writing it down, but I definitely want to recommend it, is try to avoid fractions. Okay. Now remember, we're dealing with real numbers, so theoretically we could also use irrational numbers like square roots, pi, and so on, but I'm going to be very gentle with you, so we're pretty much going to use only whole numbers and fractions. Well, as much as you can, try to avoid fractions and I'm going to show you later how to do that. So that's the first thing that you want to do. The second thing is what you want to do is you want to generate as many zeros at the beginning of each row. If you think about the correspondence between a matrix and the system, you realize that getting a zero in the matrix means that we have eliminated a variable. Okay? So we are basically using the method of elimination and back substitution on the matrix, at least in terms of the criteria, the goal that we want to achieve. So the more zeros we get, the more variables we have eliminated, therefore the closer we are to the solution. And finally, try to keep the zeros that you generate. You may end up doing a lot of work to obtain some zeros, only to get another number non-zero in the same position by doing another operation. So choose your operation so that the zeros they have constructed are not going to be lost. Now we're going to see all of this better next time in terms of what is the proper sort of formal systematic procedure for doing that in an effective way. Remember, we're looking for an efficient and effective way to solve this system, so we're going to see that next time. But through the examples we're going to see this time, you should be starting to get a pretty good idea of how that is done. Some more notable points, some more points of interest. Okay? First of all, notice that a matrix is pretty much a two-directional vector, not two-dimensional, okay? Two-directional, in the sense that a matrix is an ordered set of numbers. The only difference with the vector, the way we have seen them so far, Euclidean vector, is that those numbers are not just arranged in a row, but they are arranged over two directions, right? Horizontally and vertically, right? And so that makes it a little bit of a special kind of vector. On the other hand, a vector can be thought of as a thin matrix, right? You can think of a vector as corresponding to a single equation, right? So matrices and vectors are really pretty much in substance the same thing, right? They use the same idea. It's an ordered set of numbers which is arranged in a particular way. For vectors, we just put them all in a row. For matrices, we put them in rows and columns, okay? And this is another reason why I chose to, and I keep using square brackets for vectors and not round brackets, because in this situation the connection between matrices and vectors will become even more justified and even more evident. So again, you're free to use the other notation for vectors, but the notation for matrices with square brackets is pretty much universal. Some people will use round brackets for matrices as well, okay? But believe me, it's a lot easier to draw square brackets on a big matrix than round brackets.